Welcome back to the AI Research Roundup. I'm your host, Alex. Today we're looking at a paper published on April 15th, 2025, titled 3DAffordSplat, Efficient Affordance Reasoning with 3D Gaussians. So this paper tackles a really interesting challenge in AI, how systems understand the functional parts of 3D objects, something called 3D affordance reasoning. Like figuring out which part of a mug is for holding. Current methods often rely on 3D point clouds, which are basically sparse collections of 3D dots, and these can miss fine details. This paper proposes using 3D Gaussian Splatting, or 3DGS, a technique that represents scenes using many 3D Gaussians, which are like small, fuzzy 3D shapes, to create richer and more continuous views. The core contribution here is a new large dataset called 3DAffordSplat and a model, AffordSplatNet, designed for this improved 3D Gaussian splatting-based affordance reasoning. And if you want to dive deeper, well, the authors have put up their PyTorch implementation on GitHub. PyTorch is a common toolkit for AI development. In their repository, you'll find code for training, evaluation, and inference using their model, plus the pre-trained models and the 3DAffordSplat dataset we just talked about. All right. So Figure 1 gives us a good look at the 3DAffordSplat dataset. Part A is a wheel diagram, linking object categories to their affordances, like grasp for a mug. Part B is a bar chart, showing the number of annotations. These are labels marking the functional parts of objects. Then, Part C shows data examples. You can see it's multimodal, meaning it has various data types like 3D Gaussian splatting models, point clouds, and text, with colored areas highlighting the affordances. And Part D shows example interactions, like an AI identifying which part of a door is the handle. Now, Figure 2 really drives home why this 3D Gaussian splatting approach is beneficial, by directly comparing it to the older point cloud method. You can see for objects like a door handle or a clock, the 3D Gaussian splatting representation on the left provides much more vivid textures and clearer geometry. The affordance regions, like where you'd grab the handle, are shown as smooth, continuous areas. In contrast, the point cloud representation on the right is, well, just a collection of sparse dots, making it harder to see those fine details in smooth surfaces for interaction. Okay, so Table 1 really contextualizes the 3DAffordSplat dataset by comparing it with other existing 3D affordance datasets. What stands out immediately is that 3DAffordSplat, listed at the bottom, is the only one whose primary research subject is 3D Gaussians. All the others focus on point clouds. It also boasts a significant number of 3D Gaussian instances, 23,000 of them, and critically, it's the only dataset providing specific 3D Gaussian splatting affordance annotations with over 6,600. This combination allows for reasoning tasks, which means it supports understanding affordances based on language instructions and generating textual responses. Alright, so Figure 3 gives us a look under the hood at the AffordSplatNet model itself, detailing its architecture. Part A shows the main pipeline. You can see it takes in those 3D Gaussian splats we've been talking about, and also a text query, for example. If you want to grab this earphone, where will your palm position be? The Gaussian splats go through a series of encoders, which are like specialized processors that extract increasingly complex features from the 3D data. Simultaneously, the text query is processed by a language model to produce an "AF" token, basically a compact representation of the affordance being asked about. Then, these two streams of information, the visual features from the Gaussians and the textual information from the query, are fused together. The diagram shows components like cross-attention and channel attention. Cross-attention is a mechanism that allows the model to sort of correlate parts of the 3D object with the meaning of the text query, figuring out which visual features are most relevant to the requested affordance. Channel attention, on the other hand, helps the model decide which specific feature characteristics, or channels, are most important at any given stage. Following this fusion, the processed features go through more steps, including upsampling and concatenation, which is just combining different sets of features, and eventually into a decoder. This decoder generates something called a dynamic kernel, Think of a dynamic kernel as a specialized, adaptable filter that's created on the fly based on both the object and the query to precisely highlight the affordance region on the 3D model. Finally, this leads to identifying the affordance part and also generating a textual answer. Now, part B of Figure 3 highlights a really important component called the Cross-Modal Structure Alignment, or CMSA, module. This is used during a pre-training stage. Its job is to align the structural understanding of affordances from 3D Gaussian splatting data with the structural understanding from the more abundant, but less detailed, point cloud data. It essentially tries to ensure that the relationships between an object and its functional parts are understood consistently, whether the input is a 3D Gaussian splatting model or a point cloud. This helps the model learn better and generalize, especially to new objects it hasn't seen before. So, with that cross-modal structure alignment aiming to boost learning, Table 2 now lays out the actual performance comparisons. It essentially shows how AffordSplatNet stacks up against other models, like IAGNet and PointRefer. And these comparisons are made not only on their new 3DAffordSplat dataset, but also, it seems, on other existing point cloud affordance datasets, giving a broader view of its capabilities. Okay, so building on those quantitative results from Table 2, Figure 4 gives us a visual taste of AffordSplatNet's performance, showing how it actually identifies affordance regions on different objects. We see several examples here, like bag grasp, bed lay, and chair move. For each one, there's a text query, like, point out the areas on the chair, ideal for moving, and then you see the object visualized 4 times. These columns show the predictions from IAGNet, PointRefer, ours, which is AffordSplatNet, and GT, which stands for ground truth. Basically, the correct answer. The red highlighted areas are the predicted affordance regions, and you can generally see AffordSplatNet's predictions often aligning more closely with that ground truth, especially for fine-grained details compared to the other methods. Alright, so after looking at how AffordSplatNet performs on the dataset objects in Figure 4, Figure 5 now gives us a peek at how it handles real-world situations. We see 2 examples here, a mug and a bag. For each one, there's a question posed, like, could grasping the mug be done differently? Then we see a photo of the actual object, and next to it, the model's prediction showing the suggested grasping points highlighted in red. The model also generates a textual response, attempting to explain its reasoning for the identified affordance. This demonstrates the system's potential for practical applications beyond just simulated data. So, seeing AffordSplatNet handle those real-world objects really brings its potential into focus. The key here is that efficient 3D affordance reasoning, using those 3D Gaussian splatting techniques and the new dataset they've built. This work really helps advance how I can understand object use in 3D space from our language commands, paving the way for much more natural human-robot interaction. Alright, that's our AI Research Roundup for today. Thanks for listening. I'm Alex.